Okay, so hopefully you have tried to get this relation. If not, let us see what do we need to do. It is a very straightforward thing from this point onwards. So, we will have, when you have this relation, the only thing, the additional information that you need is that when you place it like this, which is T by B d theta by dl, the only additional information you need is that d theta by dl becomes 1 over r, and therefore, this becomes T by B r, but T we already said is equal to alpha g b square. So, this becomes tau naught becomes alpha g b by r. So, this is tau naught equal to alpha g b by r. Now, what is the meaning of this shear stress tau naught, and when we write it like this, what it is saying is that if you have a dislocation and you want to maintain a radius of with radius r, a curvature with radius r, then you need to apply a minimum shear stress, not a minimum, but this is shear stress tau naught. So, this shear stress tau naught must be applied if you want a curvature with radius r. In other words, if there is a curvature in the dislocation, then a resolved shear stress equivalent to tau naught is being applied onto this dislocation. Maybe it is being generated somewhere inside, maybe it is being applied from outside, but whatever be the source, this tau naught shear stress is being applied onto the dislocation if it has a curvature of radius r. The only unknown thing over here is alpha, and we know that from first order of approximation we can take alpha as equal to 1. So, and it varies at the most some between 0.5 to 1.5. So, you will have error in that range only, but nevertheless you would have a relation which will describe how much stress has to be applied, or the converse, how much stress is being experienced by that, shear stress is being experienced by the dislocation, if we already know that it has some radius of curvature r. So, the important thing here to note is that this tau naught can be internal or external. External, for example, when you are doing tensile test, so there is some load being applied, or when you are doing deformation, let us say in rolling, extrusion or something. So, some stress is being applied externally, which gets translated to a resolved shear stress tau naught, or internally, because you have already done deformation and therefore, there are lots of dislocation. So, because of a bunch of dislocation, a stress field is created, and because of the stress field some resolved shear stress tau naught is acting onto the given dislocation which has radius curvature r. So, this is some information about the glide force. Now, let us discuss a little bit about climb force. We will not go as much detail in climb force, because it does not have a straightforward relation the way we derived for glide force. However, there are few things that you can understand. Let us say you have a dislocation somewhere like this. So, there are planes over here, there is dislocation line, and then again there are planes like this. Now, this dislocation line, this dislocation, which is a line perpendicular to the screen, is this can either move up. So, if it moves up, climbs up, it will look something like this. Or it can climb down. So, it will become So, now you see that when the dislocation which is climbing, it can either climb up or climb down. Now, what happens when it is climbing up? When it is climbing up, then the one particular layer or row of atom which was present over here, this must go out. So, in this particular case, atoms move out, and it would mean that vacancies must move in. In this particular case, there was the extra atom layer was only up to this particular row, but now it has extended to additional row. Therefore, atoms must move in. If atoms move in, it implies that vacancies move out, and because of this there is squeezing action or expanding action which is causing the dislocation to move up or down. What you realize is that in this particular case, a lot of movement of not only the atoms take place, but also vacancies take place, and therefore, most of the time this climb process is thermally agitated or thermally governed, because when you change the temperature, vacancy concentration will increase. If you decrease the temperature, vacancy concentration will decrease, and therefore, it will cause dislocation movement in one way or the other. So, most of the time this climb force process is thermally governed, but there are also certain conservative climb motions. For example, you can have a prismatic dislocation loop, like the one where we said that the Berger vector is like this. Now, this particular dislocation loop, if it moves up or down, as you can see, in either case no vacancy is being involved, because let us say this is the extra half plane. This extra half plane can be here, it can be in a row below this, or it can be in a row above this, but wherever it is, it does not change the number of atoms in the extra half plane, which is B, or if you assume it as a extra plane of vacancies, then even in that case there is no change in the vacancy, total number of vacancies, and therefore, this can be a conservative climb. Okay, so, coming to the approximate relation for this climb. Now, here what you have to first realize is that again here you can have external stresses as well as internal stresses, which can also cause. So, the thermal agitation, you need thermal agitation, but also stresses can cause the dislocation to which will basically add additional stress for the dislocation to move, and this additional stress can be external or internal. How can be it external? For example, in creep. So, if you are doing it at very high temperature, there are stresses acting because of the load, and because of the temperature there is vacancy generation can take place, and in those cases you can have external stresses acting which will cause the dislocations to climb. Internal is the one, for example, that we discussed in the conservative climb. Now, except for the conservative climb, we have seen that creation and annihilation of point defects. In the simplest case, it will only be vacancies, but people who are familiar with steel would know that carbon atom also sits into the dislocation core, and therefore, that will also act as those interstitials would also act as point defects. So, those concentration must also change for the dislocation to climb, and therefore, creation and annihilation of point defects, vacancies, interstitials, must change for climb to take place. Now, this particular concentration can also change because of chemical forces. So, you have to take into account chemical forces along with the mechanical forces. And whenever there are chemical forces, then the equilibrium concentration of these point defects will change. So, let us say the original equilibrium concentration was C naught, then it may change to, and let us say it has changed to C, then the force it can be easily shown that the force, this chemical force can be given as B k T by omega ln C by C naught. So, the chemical forces that are acting, which because of which the equilibrium concentration changes from C naught to C, can be given by F equal to B k T by omega, where omega is the atomic volume, K is the Boltzmann constant, B is the Berger vector, T is the temperature in Kelvin, and C naught we have defined over here. So, this gives you the force, the chemical forces which will cause climb. So, this is the fundamental relation for the climb forces required for the climb motion. So, now we have looked at the fundamental derivation of forces that can cause the glide motion and the forces that can cause the climb motion. These are the two primary way that a dislocation makes a movement. Now, when the dislocations are moving, then you can realize that it will also interact. Next step of understanding in terms of motion is how do they interact. So, there may be one dislocation because of which there other dislocation will experience a stress and that will cause some force acting onto it, or there may be a bunch of dislocation because of which there may be stresses acting onto another dislocation. So, let us say that we have a dislocation standing over here. So, this is the one that is causing the stress field, and this is another dislocation whose motion we want to study. Now, this one will create certain stress field. So, let us say these are stress contours. So, there will be sigma x y z, and this dislocation this dislocation will have some line vector E. It will also have some which can be resolved as E1, E2, E3, where 1, 2, 3 can be taken as x, y, z direction, and it will also have a Berger vector. So, Berger vector can be resolved as B1, B2 and B3. Now, this so far what we have said is that this stresses are acting onto this dislocation 2 because of one dislocation. However, what we are taking into account is just the stress field, and this stress field can be generated by not just one dislocation, it could be a bunch of dislocation. So, let us say there is this bunch of dislocation because of which there is some stress field again which will have the form sigma x y z. So, this is a matrix quantity sigma x y z, and because of that you want to calculate the stresses onto 2, for which we know E and B. Now, this is given by what is called as Kohler relation. So, what is this Kohler relation? It describes the forces that we want to calculate on 2 because of either the case of 1 or 2, but what we have is basically stresses acting because of or arising from different dislocations. So, it will be given like this. So, like we said, this E belongs to dislocation 2. This is the line vector. This Berger vector belongs to dislocation 2. So, dislocation 2 is the dislocation onto which we want to find the forces acting, and again you see that we are calculating as force per unit length. Now, what is this stress? Where is this stress coming from? This stress is arising because of dislocation 1 or bunch of dislocation or any other source. So, we can call it simply sigma from other sources. We have already seen how to calculate stresses from a single dislocation. So, if it is a single dislocation, we can directly find at a particular distance x, y, z what will be the stresses, and then we can put it over here sigma dot b cross E to get the forces acting per unit length onto the dislocation. For a simple case that we will discuss here to begin with, let us say we have a for edge dislocation whose line vector is given as 0 0 1, meaning it is along the z direction. Would you be able to show that the force acting onto this there is another term here. So, force will have x, y, z component. So, this is f x, this is f y, and this is f z, and it goes without saying that when we have written it like this, it means that the Berger vector of the dislocation onto which we want to calculate has Berger vectors b 1, b 2 and b 3. However, since the dislocation is oriented along z, the third Berger vector b 3 does not appear in over here. Now, if we further make the simplification that b 2 is equal to 0, what does it turn out to be? B 2 equal to 0, it means that we have the Berger vector only in the perpendicular direction to the line vector. So, it is a edge dislocation. So, we can say that Berger b 2 is also equal to 0, b 3 does not matter, but we will say that it is also equal to 0, and therefore, f x by L would come out to be. So, I am missing something. Make note of this, I had earlier mistakenly written at sigma y y, it should be sigma y x. So, it is sigma y x b 1 and now we can simply put sigma y x, which we know what the relation for which we know from our earlier derivation. So, the sigma y x is the stress because of a particular dislocation at a given distance x and y. Therefore, it turns out to be x square minus y square and you can also find so, this is the f x per unit length, that is the glide force, So, on dislocation 2, this is the glide force that we have calculated, and this is the climb force that we have calculated. And since we have expanded sigma y x like this, it means that we are assuming that this stress sigma is arising from a single dislocation, from single edge dislocation. Now, at this point it would look like how did we arrive to this relation, but this F by L equal to this, and I would very much like that you do it on your own. I will just what I will try to do here is show you the full mathematical multiplication which gets us to the relation sigma dot B cross E. Not to derive the relation, but how to expand the relation sigma dot B cross E. So, our next step, once we have looked at one example where we were looking at the forces acting on edge dislocation, is the next step is to look at the full expansion of the relation Peach-Kohler relation sigma dot B cross E. So, coming back to our Peach-Kohler relation, which was okay. So, now if you look at it, there are two components to it. First, what we need to do is do this dot product, where sigma is a tensor and B is a Berger vector. So, you can realize that when you do this multiplication, what you will get is a vector. So, this vector will be cross multiplied with this vector, and there again we will get a vector of force, where we will have f x, f y and f z. So, first let us look at the expansion for sigma dot B. This can be in a summarized way, it can be written like this. Which will expand to like this. So, you can see that this is sigma I j into sigma B k. So, we are looking at in those forms. So, what you would see is that what we have now obtained is a vector which gives us sigma dot B. So, this matrix sigma has now been taken a dot product with B, which is given by this condensed equation. When we expand it, this looks like this. Now, what we need to do is we want the next step we wanted is, now that we already have this which is a vector. So, we multiply this vector, take a cross product of this vector with E, and this is again in overall the column vector would look complicated, but the multiplication is straightforward if you know the matrix multiplication, and it will come out to be Okay, so this is the full expanded form of sigma dot b cross E. Once if you are in a position to write your sigma matrix in terms of sigma 1 1 1 1 2 1 3 2 1 2 2 2 3 3 1 3 2 3 3 and similarly your Berger vector b 1 b 2 b 3 and line vector e 1 e 2 e 3, then this thing just boils down to this particular line vector. And again it may seem like again very imposing and intimidating, which has 6 terms in each of the rows, but again if when we make certain assumptions about our dislocation, it quickly boils down to a very simple number. For example, we had shown earlier that our line vector was 0 0 1, which means epsilon 1 and epsilon 2 would become 0, and when you do that epsilon 1 0, epsilon 2 0, epsilon 2 0 here, and therefore you would what you would get so again 1 and 2, this will also turn out to be 0, this 0, this 0. What you will be left with is just this quantity and this quantity, and this will also boil down to 0. So, as you can see, just by making one simple assumption that your dislocation line is along 0 0 1, which does not take away any information from your system, you are able to simplify this to just 2 terms. Right now it has, if you look at it, 2 plus, if you take this as one big term, then it has 6 terms. So, from 6 terms it boils down to 2 terms, and even in those 2 terms, if you look at sigma 2 1 2 2 b 2 and all these expansions, what we have is dislocations. If we assume that what we have is the edge or a screw dislocation, then again you can say okay, sigma 2 1 or 2 2 would, for example, in the case of our screw dislocation, all your 1 1 2 2 and 3 3 will go away, and therefore you will again reduce these smaller number of parameters, and you will be able to easily obtain the final relation. So, coming back to our first problem, not the problem, but the first example that we looked at, where we said that we have to find the force on a dislocation, and we assume that the starting force, the stress is being generated because of edge dislocation. We showed a relation. Now, you can obtain that directly from here. Like I said, you take epsilon along 0 0 1, and therefore what you are left with is only these 2, and over here too what we will do is, so what we have is and we will say that Berger vector is equal to therefore, you would see that f by L is equal to sigma 2 1 b 1 sigma 1 1 b 1 and the z quantity is 0. So, this is f x, f y, f z. So, what we are talking about here is a edge dislocation. So, we are still very general. We have just said that the line dislocation is along 0 0 1, and since it is a edge dislocation, we can talk about 1 0 0 as the Berger vector, and when we have this Berger vector, our force per unit length boils down to this. Just from that intimidating matrix, we have come down to just small 2 term matrix, not even a matrix, but a column vector, and therefore it is much more easier to calculate over here. And now we can, like I said, 2 1 you can take as y x for a starting dislocation, and therefore f x by L can be written as g b square by x and f y by L is equal to minus So, we will leave it at this point. We will come back to the discussion on forces in the next lecture.